There we are. Right, so question 1, a car's travelling at a speed of 20 meters per second. The table contains values for kinetic energy and momentum. There's a little trick you can do here. You can do this by estimation, but there's a little bit of reverse engineering you can do. You know that momentum is mass times velocity. So if that's the case, then you can actually get some reasonable values for the mass of the car out. So for example, if that's going to be momentum over velocity. So if we take, that's 30,000 divided by 20, well, that's 1,500 kilograms, which is a reasonable value for the mass of a car. If I try to do the same here with the 500, with the, sorry, 5 million, that's 5 million divided by 20, that would give you to 200, something like, be about 250,000 or something like that, which is obviously way, way, way too much. That's not a realistic value. So it's got to be either this one or this one. Now you know it's 1,500, you can use kinetic energy is a half mv squared. So it's a half times 1,500 times 400, and that comes out to be 300,000. Okay, which is going to be that one. The only row that's got them both correct is A, and that's how you do it. Okay, so the next one, you've got a unit of resistance. Remember, it's base units. So you're using the formula R equals V over I. Well, V is energy per coulomb. The energy is work, is same as work done, so that's force times distance. And we know that force is MA. So what we're saying is that the units for resistance are the units for V, which is going to be the, V is going to be Q, well, Q is amps seconds. Okay. Then energy is force times distance, force is mass times acceleration. So we've got mass times acceleration is kilograms meters per second squared multiplied by meters. Multiplied by meters. Okay, and that gives you the energy. So then we just got to tidy it all up. So the units of resistance is kilograms meters squared seconds to the -3 times amps to the -1. So that looks about right. So let's see if it's any of these then. Kilograms on its own, yes, meters squared. So it's not that one, not that one, not that one. Seconds to the -3, there it is, it's B. So the next one says which list contains scalar and vector quantities. So we're looking for things that have direction, things that don't. So all of these are vectors there. Area, current, force, and work. That has got, that's a vector, force is a vector. We know that work is a scalar, so it's got to be B. Won't spend too long on that one. And then you've got to do two vectors, P and Q, and you want to work out the vector P plus Q. So what you're doing is you're taking your vector Q and you're putting it onto the end of vector P. Like that. Making it roughly the same length. So let's just go to centimeters. So what do we say? 3 centimeters. So that's 3 centimeters. Looks like that. So the resultant is going to be from start to finish, like that. So that's your resultant. So we're looking for one that's going slightly down and quite a long arrow. So that's going to be A. Okay. Now the next one, on to number 5. We've got students take readings of a volume of a liquid using 3 different pieces of measuring equipment. And they want to know if it's precise or accurate. So This one, it's not very precise because there's a wide range of readings. It is, however, accurate because the peak, the average, is going to be about where it's going to be where it is. So that's accurate. This one, well, most of the readings are very close together. So that's precise, but they're all below the actual value. So that's precise, but not accurate. This one looks like it might be accurate, but it's not. If you look at the area under the graph here and the area under the graph here, your average V be somewhere over there-ish. So it's not really very precise because it's a wide range of readings. It's not accurate because the average is quite a long way away. So remember, the average isn't just where the peak is. So A shows that there's only one precise measurement, only one precise set of measurements, and only one accurate set of measurements. Next one is a sprinter runs a 100-meter race. A sprinter has a constant acceleration from rest of 2.5 meters per second squared until they reach 10 meters per second. The speed then remains constant until the end of the race. So what time does it take them to run the race? Now, this is quite a tricky one. So what are they saying here? They're saying that if you've got, the best way to do this is graphically. If you've got a velocity time graph, you know the distance of 100 meters will be the area underneath it. So it says it accelerates at 2.5 meters per second squared, okay, up to 10 meters per second. So that time there, the acceleration time is going to be 4 seconds because it's 10 divided by 2.5. So the first 4 seconds is the time it takes for the sprinter to get up to their maximum velocity of 10 meters per second. Okay, now do we know how long it takes? No, that's what it's asking us. So it wants to know what that overall time t is. So what we do is we work out what this distance is first. So this distance is 1/2 times 10 times 4. And if that's the case, that's going to be 20 meters. So this area here has got to be 80 meters. So if you're traveling at 10 meters per second, that has got to be, let's double check that. 1/2 times 10, that's 5. 5 4s are 20, that's okay. This one here has got to be 8 seconds. Because it's got 80, so 8 multiplied by 10, it's the area of this rectangle. So that's got to be the 8 seconds there. So it's going to be the 4 seconds, so that's going to be 4 plus another 8 is 12. So the time it takes them to run the race is 12 seconds. And there we go. That's quite easy. It's easy once you actually sort of work graphically on this one. So the next one says you've got a resultant force of 10 newtons acting on a body for a time of 2 seconds. Which graph could show the variation of time t with the momentum of the body? So it's got a resultant force of 10 newtons acting for 2 seconds. Okay. So what we're looking at is the idea that the momentum p, the rate of change in momentum. So the change in momentum is equal to force times time. So if it started out at 20 meters per second, at 20 kilograms meters per second, if that was going for 2 seconds, that would be 20. So that 20 could go down to 0. So it could well be B, it's not A. So we're looking for a change in momentum of 20. Well, these two are not changing by 20, so it's got to be B. The next one is the acceleration of freefall on the surface of planet P is 1/10 of that on the surface of Q. So on the surface of P, the body of mass of 1 kilogram and a weight of 1 Newton. What are the mass and weight of the same body on the surface of planet Q? So you've got to think very carefully. So we know that the acceleration is 1/10. So we know acceleration of P times 10 is the same as the acceleration on Q. It's worth actually writing it out as a mathematical ratio. So on the surface of P, the body is a mass of 1 kilogram and a weight of 1 Newton. So the mass is still going to be 1 kilogram. That's going to stay the same. So that's not right, and that's not right. The weight, if it's 1 Newton on the body of P, then it's going to be 10 Newtons on the body of Q. So it's got to be that one. So 8, the answer was, double check, have I got that right? No, because I said that's wrong. It's got to be that one, it's got to be B, isn't it? Okay. Now, two bodies traveling along the same straight line collide, perfectly elastic collision. Which statement must be correct? It's either right or wrong. So I'm not going to spend time dwelling on it. It's the idea that the relative speed of approach equals the relative speed of separation. Remember, that's one of the definitions. That's one of the key features of elastic collisions. Then you've got two identical spheres, X and Y. Initially, X moves with speed directly towards Y. They collide elastically, so we're thinking about maybe the same thing here. So which one of these has got to be correct? So we know the speed of approach is going to be just v, because that's stationary. So we know the speed of separation in total has got to be the same. So this one moves the speed half v to the right, to the left. So that's a possibility, I suppose. Okay. That one is unlikely because we're not conserving momentum, are we really? Are we conserving momentum here? No, we're not. So that's not possible either. So we're not conserving momentum with A. We're not conserving momentum with B. With C, are we conserving momentum? Again, no, because that's implying zero momentum. So afterwards, so it's got to be D. Okay. Number 11, a positively charged particle, the negligible mass is moving at constant velocity. I think we did something very similar to this in a revision lesson recently. So we've got the particle moving through. Short time later, particles over here, which represents the forces acting on the particle. Well, if we think about it, the only force in town here is the force pulling it down to the negative plate, like that. Okay, there are no other forces acting on it, okay, because it tells you it's doing it in a vacuum, so there's no air resistance, there's nothing else there, apart from gravity maybe, but that's still going to pull downwards as well, so it's just got to be D. Right, number 12, uniform rectangular board is supported by a frictionless pivot, so this is a centre of mass and moments question by the looks of it. The two forces act in the plane of the board. Force F acts at the corner Q, and force 2.5 F acts at the corner R. Okay, so it's labelled in this diagram here. The perpendicular distance between the line of action of the forces F and point P is 20 centimetres. The board is in equilibrium. What is the possible area of the board? So what we're really doing is we're actually finding out that value there. Well, if it's in equilibrium about that point, because it's pivoted, if it's in equilibrium, we know that that 20F has got to be equal to that X times 2.5F. Okay, the F's cancel, so it's 20 over 2.5. Alexa, what's 20 over 2.5, please?
20 divided by 2.5 is 8.
That's 8. That's going to be 8 centimeters. Okay. So 20 times 8 is going to be, well, 2 times 8 is 16, so it's 160. So it's 160 square centimeters. I'll double check that. Have I got that right? Have I done that correctly? Let's see. Have I done...
I think that like you have to add the two sides. So it's 20 plus 20 multiplied by 8 plus 8. So it's 320 centimeters squared.
You are absolutely right. Well done. Well done. Well done. I'm glad we're awake. Excellent. Thank you. So I'm just going to go back to my thing. You're absolutely right. That's not correct, is it? Because all I've done there is I've worked out that area. It's 4 times that. So it's that one. Okay, let's move on. Excellent. Well done, Ikenna. Now, number 13. A kite is in equilibrium at the end of a string. The kite's got 3 forces acting on the weight W, the tension T in the string, and the force F from the wind. Which vector diagram represents the forces acting on the kite? So we've got to think about this a little bit. Well, if we think about it, we're going to have the string pulling in that direction. So that one's wrong, okay, it's acting on the kite. So the string's going to be pulling it in that direction. We know that the weight is going to be pulling it downwards. So what we must have, therefore, is the basic idea that the whole thing is in equilibrium. So there's a resultant force from the wind, which is going to be pushing on the kite in that direction. So that's definitely not right either. So if we then put the arrows end to end, we end up with A as being the answer. Right, number 14. The density of air in the atmosphere changes with height h above the surface of the Earth. Which one shows a variation of height h with a pressure? So if we think about it, the answer is going to be C. It's going to be something like that, isn't it? Okay. It tells you the density of the air decreases as the height above the surface increases. So it's kind of like inversely proportional. So number 15, the bungee jumper is on a platform over a river, attached to an elastic rope, 20 meters long. There's a lot of information here. It says it's the rope's 20 meters long when it's unstretched. He falls, his lowest point is 30 meters. So the extension is 10 meters. The initial gravitational potential energy of the jumper is transformed into other forms during the jump. Which other forms of energy does the jumper and the rope have when the jumper has fallen halfway? So it's fallen halfway. So he falls 30 meters, but the cord hasn't started. The cord hasn't started to stretch yet. And that means at the lowest point, you'll think about what he's actually doing. When he gets to the lowest point, he'll have stopped before he gets pulled back as he's accelerating upwards. So before his velocity changes to an upwards velocity. So halfway down, we know it's kinetic energy only. The lowest point, well, kinetic energy is going to be 0. So it's got to be D. Number 16, a cylinder contains a fixed mass of gas. The gas at constant pressure of 1.3 pascals expands from 900 to 1100 centimeters cubed. Hello, centimeters cubed. Got to be careful here. So the change in volume, because we know that the work done is P delta V. We can do that in our sleep. But delta V is going to be, well, 1 centimeter is 100 multiplied by 100 multiplied by 100. Okay, so that's 10 to the power of 6. So we know it's going to be 900 cubic centimeters. 900 times 10 to the power of minus 6. Okay, that's going to be the smallest volume. So it's going to be 1100 times 10 to the power minus 6 minus the 900. gives you the change in volume. So that's going to be 200 times 10 to the minus 6. Plug it into your calculator. So it's 200 times 10 to the minus 6 multiplied by 1.3 times 10 to the power of 5. And that should give you a value of 26. Okay, it's easy enough. So then you're shown an object thrown into the air, which graph shows the gravitational potential energy varies with the height above the ground. A lot of people think it's time. Oh, if it's time, it's going to be following that one. Not necessarily, okay? So we're thinking about what happens to its gravitational potential energy varied with height. Well, we know, as long as we're not sort of going off into space, we know that delta GPE equals mgh, so it's proportional. So the answer is simply A. A lot of people got that one wrong when it was a real exam. So then a car of mass of 1,800 kilograms accelerates in a horizontal road, so its speed increases from 20 to 25. You want to work out the power output of the car's engine. So you've got to be careful here. It's basically, it's the change in kinetic energy over time. So the change in kinetic energy is a half times 1,800 multiplied by, now it's 25 squared minus 20 squared, okay? So that gives you the change in kinetic energy. Divide it by 5.4 and you get a number that's round about sort of 38,000, okay? Okay, simple as that. Number 19, not going to spend too much time on. A variable force is applied to ensure constant power is supplied to a train. Which graph best shows the variation of the force F applied with the velocity V of the train? So to think quite carefully here. If we think about it, the force applied shows the force applied with the velocity F of the train. So it's going to be A. Okay, think a little bit carefully. Have I got that right? Well, if I think, am I doing this right? So I'm thinking about it. Yeah, that's that would look, that would be right. Okay. Right, let's move on. Excuse me. Now, the metal cylinder is able to withstand a compressive force of 4,000 newtons without deforming plastically. So the cylinder's cross-sectional area A, what would be its elastic limit as stress is applied? Excuse me. Excuse me, a bit of hay fever. So we're thinking about it carefully. So if we're looking for the stress, and then we've got the area. So let's think about it. If it's got, just see what we're given cross-sectional area A. So we know it's 4 kilonewtons. We're assuming that's going to be sort of the limit. Okay. So if we're working out the stress is going to be force over area. So it's going to be 4,000 over A is going to be sort of the maximum stress you can put on it. So if we're thinking about it, the stress times the area is 4,000. So if we just multiply these together, you find the one that comes to be 4,000, I reckon, that one. Now, number 21, not going to spend time on this. A wire has both elastic and plastic properties. When it's slowly loaded, the extension varies as shown OXY. Remove the load, goes from Y to Z. So it's gone past the proportional and elastic limits, creates areas P, Q, and R on the graph. Okay. Which area represents the maximum elastic potential energy stored in the wire? Now we've got to think about this. If it's stored, that means it comes back out. So in other words, as the wire goes back, the energy dissipated is that bit. So it's going to be R. A lot of people thought it was Q plus R, but it's not. Number 22, a progressive wave on a wire has a frequency of 10 hertz. 2 points on the wire separated by a distance of 0.25 meters have a phase difference of 22.5 degrees. What's the maximum speed of the wave? So if we think about it, V equals F lambda. Okay, we know lambda, we know F is 10 hertz. So 2 points of the wire, the distance. So it's a maximum speed is when these two are the highest number possible. So this one is constant, it's 10, so we're looking for the highest value, highest reasonable value of wavelength. That's going to be the longest wave. So that would be 22.5. So to work out how much of a wavelength that is, that would be about 22 point, that would give you the portion of the wave, because that's whatever 0.25 is. So Alexa, what is 360 divided by 22.5? Alexa, what is 360 divided by 22.5?
360 divided by 22.5 is 16.
So it's a 16th of the wave. So it's 0.25 times 16 is 4 meters. So the wavelength is 4 meters. So the speed is 10 times 4, which is 40. Easy as that. The next one, guitar string is plucked. It causes a longitudinal sound wave in the air as shown. The speed of sound is 340 meters per second. Was the approximate frequency of the sound wave shown? Well, we're looking for a wavelength. There's your wavelength going from there to there. So 23. So that's going to be 0.5 meters. So we know that the frequency is the speed over the wavelength. So that's 340 divided by 0.5, which is going to be 680. There we go. 23 was B. 24. The sound from a loudspeaker placed above the tube causes resonance. So we're looking at standing waves. The speed of sound in air is 340 meters per second, and the frequency is what we want to find out. The frequency is what we want to find out. So what we're doing here is, if we're working out the frequency, we've got to work out what the wavelength is. If that's 60 centimeters there, that is basically a third of 60 centimeters. So that is going to be 40 centimeters, which is 0.4 meters. So if that's equal to that, then it tells you that the wavelength is going to be, well, that's one wavelength like that, isn't it? So that's half of it. So that's 0.8 meters. Okay, so the frequency is the speed over the wavelength, which is 340 over 0.8, which should come out to be 430 hertz. Easy as that. Next one says a police car has a two-tone siren emitting frequencies of 700 and 1000 hertz. The police car is traveling at the speed of 40 meters per second towards a stationary observer. Speed of sound in air is 340 meters per second. What's the difference between the two frequencies of the sound that's heard by the observer? So we're looking for the formula which gives you which refers to Doppler effect. Now, if I try and look at it, have we got it on the formula sheets? We've got it here. Here it is. That's the one we want. So we know the frequency observed is going to be FSV over frequency of the source times the speed of sound plus or minus V plus or minus Vs, which is the speed of the source. So we know that the change in observed frequency is going to be FSV times 1 over V plus Vs minus V minus Vs, I apologise, V minus Vs minus 1 over V plus Vs. Okay, so what we end up with is basically we know Vs, we know V, plug them all into your calculator, and you end up with something in the region of 340 hertz, according to my calculations. Right, so you then got a surveyor's device, emits a pulse of light, it's reflected from all 150 meters away. What is the time taken for the pulse to travel from the device to the wall and then back to the device? So it's from the pulse to the wall, then back. Well, we know that distance is 300 meters, and we know it's light. So we know the speed of light is 3 times 10 to the power of 8 meters per second. How do we know that? Well, it's on the formula sheet. Okay. So what we want to do is we want to work out the time. Well, we know that if speed is distance over time, then time is the distance over the speed. So it's 300 over 3 times 10 to the power of 8, which comes out to be about 10 to the power minus 6 seconds. So that's 1 microsecond. Progressive sound waves of a wavelength of 20 centimeters. So that should become automatic by now. They enter air columns in closed and open pipes. In which pipes are stationary waves formed? So if we think about it, you've got to think about the wavelength. What's 20 centimeters to that weight compared to that wavelength? Well, that's going to be 20 plus 15. Okay. So we're probably not going to get a stationary wave in there, because what they're assuming is that that's got to be an antinode there, but the antinode would probably be a little bit beyond it. So it might do, because it depends what the end correction is. But let's have a look at Q. It might do, because that's an end correction, isn't it? This one here, the wavelength is 0.2, so that would be an antinode here and an antinode here. So I've got to think about this. In fact, I've done this slightly wrong. I do apologise. Not thought this one through. It's a genuine mistake, which I didn't remember from last time. Because what I'm doing here is I'm saying, well, okay, here we've got an antinode and a node. We know that we've got a fixed node here. So that 20 centimeters, that's 2 wavelengths. So that's 1 wavelength. So really, what we have in between it is we'd have a node there. If there was a stationary wave, there'd be a node there, and another node that would be at 10, 20, 30. There'd be a supposed one at 40, so there'd be an antinode here. Try and get this right. So this one would form, haven't drawn this very well. So we got 10, 20, 30, 35. So that would be an antinode. So yes, you'd get your stationary wave produced there. So this one, again, we'd have an antinode here. So you'd have another antinode at 10 centimeters, 20 centimeters, 30 centimeters, 40 centimeters, and so on. So that would then be, so that would also have an antinode at that end. So it was definitely P and Q. Number 28, we're nearly done now, only about less than 10 minutes left. What happens when waves pass through a gap equal to the wavelength? We know that they will more or less diffract. So there is diffraction. So the wavelengths that should stay the same is probably the correct statement there. Number 29, we've got two microwaves. So this is two source interference. They produce a phase difference of 180 degrees. So P is in antiphase with Q. So be careful. At the point S, there is a minimum in the interference pattern. So which expressions show the path difference? So if we think about it, if that was a minimum, normally if they're in phase, the path difference would be half a wavelength. But this time, if the path difference is an exact number of wavelengths, then there'd be an antiphase. So that would actually be a minimum just there. So the answer is A, because they're in antiphase. So they'll only interfere constructively when the path difference is half a wavelength. Number 30, you've got a parallel beam monochromatic light. So this is now diffraction gratings. So it says the angle between the two second order diffracted beams at P1 and P2 is shown. Okay. Now, if we think about it, we've got to think very, very carefully. What's the spacing of the lines on the grating? My goodness. So we know n lambda equals d sine theta. We just got to work out what theta is in terms of the angle alpha. So we know that n is 2 because it's second order. We know that alpha, well, this angle is the diffraction angle. And if that's the diffraction angle, then theta is a half alpha because it's symmetrical. So what we end up with is 2 lambda equals d sine alpha over 2. So we just rearrange to make d the subject. It's 2 lambda over sine alpha over 2. So which one is that? That's going to be C. Right, electric fields next. So we're down to our last 10 questions. A flat plate's positively charged, and the curved plate is negatively charged, which diagram shows the electric field lines. Remember, they should always be perpendicular to the surface, and they should always be going from positive to negative. So the answer on 31 is C. Two metal plates are connected to an DC supply. The two plates are moved towards each other at constant speed. Maybe assume the electric field between the two plates is uniform. Point P is midway between the two plates. Which graph shows the variation of time with the electric field strength E at point P? So if they're being moved together at constant speed, what we're doing is we're looking at the idea that the distance between them is changing uniformly. Now, when we think about it, we'll work that out. We know the electric field strength is going to increase. And we know that therefore the electric field strength is going to increase, and it's going to increase sort of more rapidly. Okay? So the answer is D, 32. Now, number 33. Which two units are used to define the coulomb? 1 coulomb is 1 ampere, 1 amp second, isn't it? So that's 33 is A. Number 34, you've got electrical device. This one was hard. A lot of people struggled with this one. So you have to take this in 2 steps. It tells you the power dissipated by this resistor is 4 watts. And it tells you its resistance is 20 ohms. So you could work out the current flowing through it. So the power is I squared R. So we know that I is going to be the power divided by the resistance, all square rooted. So we're looking at the power divided by resistance square rooted. So the power is 4, the square root of 4 over the resistance of 20. which is the square root of 0.2. Okay, I'm going to leave it there. I don't have to work that out for a second. I can do that later. So that tells me the current, and it's the same as the current flowing through this resistor, through this variable resistor. And okay, I'm just going to double check that. Yeah, okay. And so now I want to work out the total current. Well, I could work it out for the whole circuit, couldn't I? I could work out what the total resistance is. The total resistance is going to be the EMF over the current, which I've worked out. The EMF is 16 divided by the square root of 0.2. Okay. And then I could work out, and then all I need to do is then subtract the 20 ohms resistance there. And if you plug it into your calculator, you should get, bear with me, I'll do that on my calculator. You should get 16 ohms, I believe. Now, the next one is a wire of length L is a resistance of R. The cross-section area of the wire with circular radius R. The second wire is also cross-section radius, the same material, resistance of R over 2. So it's half the resistance. Okay. Now it says what could be, so it's going to, which one of these would give half the resistance? Well, if you've got half the radius, then you've got a quarter of the area, and you've got half the length, so you can have 4 times resistance due to the area, but then halve it to make it 2. So that's not right. The next one, if you're going to have half of the area, which means you'll have twice the resistance. You'll have half the length, which means you'll have the same resistance, but we want half the resistance. So here we've got a resistance, we've got twice the area. Okay, so that means you'll have half of the resistance times twice the length will just give you the resistance. So it must be this one. Twice the radius means you have 4 times the area. So you'll have a quarter of the resistance, but you'll have twice the resistance due to twice the length. So a quarter twice is half. Half R, it's got to be that one. Right. Next, we've got battery of negligible internal resistance, maybe connected between any 2 points. Which of the connections will give the largest current and the smallest current? So the one that will give the largest current will obviously be the smallest resistance. So the best way to do that would be to connect it across PQ, because that way the total resistance will be below 3 ohms. So it's likely to be that one. And to get the highest resistance, well, what we'd want to do is put it across the 2 corners, which would give you the highest possible resistance in both branches, which would be probably between here and here, because there we've got 9, you've got 9 there, so that would be 4.5 ohms. Put it across here, you've got 8, so we know the resistance will be less than 8, so it's got to be QS. So the answer is B. Kirchhoff's second law is a consequence of a basic principle. Kirchhoff's second law is the idea that the energy in an electrical circuit is conserved. That's a basic bit of knowledge. Last bit. So we've got 2 cells investigating a potentiometer. Which statement is not correct? Okay, so number 38. The answer here was C, because all the rest were correct. Okay, so we know the potentiometer balance points at 0. The potentiometer balance point results in 0 current. That's part of it, part of what potentiometer does. The balance point, the current through resistance R is both the same. That's true. And the value of the EMF of each of the cells is X and Y. It's got to be less than 6 volts, otherwise it doesn't work. You don't get a balance point. So, number 39, a nucleus undergoes beta plus decay. One of the products is a neutron. What are the 2 other products? So, that's a little bit naughty, that. I don't think, yes, yeah, that's right. One of the products is a neutron. So, produce, if it's beta plus, it's an anti-electron or a positron, and therefore it produces a neutrino. Number 40, a certain type of hadron has 0 charge. It's comprised of a down quark, a strange quark, and one other quark. So if we think about it, it's got 0 charge. We know a down quark has got a charge of -1/3, and a strange quark also has a charge of -1/3. If it's going to be neutral, it's got to be 2/3, so it's got to be an up quark, and that's how you do it. Okay, guys. Right, I'll stop there because I think we're pretty much at the end of the lesson now. I bid you a good weekend. Have a look through any of the questions you couldn't do.
Okay, sir.
Okay, and have a good weekend. Well, otherwise, if you've had to go at the paper already, you know what? Pat yourselves on the back and take the weekend off. All right, I'll see you all next week.
Thank you, sir.
Okay,
See you,
bye.
sir.
Bye, everyone.
Bye.